Hi everyone, welcome back. We're going to be talking today about inverse Laplace transforms, which is the last step we need in our methods for solving differential equations with the Laplace methods. If you'll recall, we had a bit of a schematic that we were going to start with a problem in the time domain, transform it over to the Laplace, and then solve somehow, get a solution over in the Laplace world. And then the last step was to translate it back. So Laplace, solve, and then we'll be doing inverse Laplace to get back to the time solution over here. So this is the last step that we're working on. We are trying to do this last bit to translate whatever solution we get on the Laplace side back over to the time side that we need the solution in. And so this is what's called the reverse Laplace transform. Unfortunately, there's no simple formula for this. We can't just plug it in and compute an integral like we can for finding the Laplace transform itself. The inverse Laplace transform, or the reverse Laplace transform, does not have a formula like that. Instead, we have to rely on our experience and the things that we know, do some table lookups, things like that. So it's similar in a lot of ways to things that we would do with integration as opposed to differentiation. So let's see how this would work. So the first thing we'll try to do a simple inverse Laplace transform, find the function whose Laplace transform is 10 over s squared. So the thing that you want to do is look at this and see if it fits into any of the schemata we have for known Laplace transforms, and it's close to one of them. So we would recall that the Laplace transform of t to the n is equal to n factorial over over s to the n plus 1. So if we can make f of s look like that, then we will be in business. So that's exactly what we're going to do. So we'll start with, we're trying to find the inverse Laplace transform of 10 over s to the 4th. So what is that? Well, let's try and break things down. Do this pretty formally at this point. So it's 10 times 1 over, and it's going to be s to the 3 plus 1. All right, so we haven't really done too much there, but you'll notice that this s to the 4th we're thinking of as 3 plus 1 because that matches with this form that we have here. We need to make the tops match also, so we're going to need to make it 3 factorial up in the numerator here. So we do that with a simple multiplication and division. This is the inverse Laplace transform of 10 over 3 factorial times 3 factorial over s to the 3 plus 1. And now Laplace transforms and inverse Laplace transforms are linear, so we can pull out the 10 over 3 factorial, inverse Laplace of 3 factorial over s to the 3 plus 1. And so that's 10 over 6 times the inverse Laplace transform of 3 factorial over s to the 3 plus 1 is t cubed. So we get that the inverse Laplace transform of 10 over s to the 4th is 5/3 t cubed. That's how it works. Of course, you can always check this if you integrate 5/3 t cubed e to the minus st dt. That's a little bit wearisome because you're going to have to do integration by parts 3 times to make that work, but you can do it. But we want to get confidence with this method because we don't want to have to do that check every single time. All right, so let's continue trying more examples of this. Let's take, there we go. So now let's try to find the Laplace transform of, the inverse Laplace transform of 3 over s squared minus 6s plus 10. So again, we're looking for something that looks kind of similar to this. And the one that I'm going to ask you to recall here is that the Laplace transform of sine omega t is equal to omega over s squared minus omega squared. So hopefully we can get it to look kind of like this. So what we're going to do here is we're going to go back to algebra and use the technique of completing the square. All right, so a blast from the past. We have 3 over s squared minus 6s plus 10. To complete the square in the denominator, we need to figure out what we need to add to this polynomial to make it a perfect square. The way we do that is by taking our number here, our coefficient, dividing it by 2, and then squaring it. Right? So the formula is b over 2 squared is the thing that we have to add and subtract. So we will add a plus 9. We already had a plus 10. And then, of course, we also have to subtract the 9 in order to make this an actual equality. And once we've done that, now we can rewrite this as 3 over s minus 3 squared plus 1. Now, this looks pretty similar to this formula, but not quite. We have s minus 3 instead of s. How are we going to deal with that? Well, then we have to recall another one of the rules that we have, one of the shift theorems. Right, so we had a shift theorem that says that the Laplace transform of e to the alpha t times a function is equal to f of s minus alpha. So we just need to look at what function can we do where we plug in s minus 3. So we just need to know what is the inverse Laplace transform of this thing without the shift. So the inverse Laplace transform of 3 over s squared plus 1, looking back at our formula there, well, this is equal to 3 times 1 over s squared plus 1. So that would be the function 3 times sine t. So, using the shift theorem, the inverse Laplace transform of 3 over sine minus 3 squared plus 1 is 3 sine of t. Well, sorry, let's do it in the same format as what we have there. It's equal to e to the 3t times sine of t. Right? Because if we have a shift on the Laplace domain, like we do here, then what we get is the Laplace transform without the shift, or the function that would have that Laplace transform without the shift, multiplied by e to the alpha t, where alpha is the amount of the rightward shift. So this is our final result. That is the function whose Laplace transform is the thing that was given above. All right, so completing the square and recognizing what kind of thing we are starting with are key for this process. All right, so let's try again. All right, so let's try now to find the Laplace transform of this same function, but instead of 3 on the top, we have an s on the top. So again, we look for similar things that we've seen before, and the similar thing that we're going to have this time is that the Laplace transform of cosine of omega t is equal to s over s squared plus omega squared. So you're hopefully starting to see that knowing the realm of all of the possible Laplace transforms, knowing what's in that table of Laplace pairs is going to be very important for us. All right, so knowing this, we can rewrite the thing we're trying to find the Laplace transform of using completing the square. We have s over s squared minus 6s plus 10, and this is the same denominator, so it works in the same way. We get s over s minus 3 squared plus 1. Right, that's a little bit messy there, but hopefully you can read it. S minus 3 squared plus 1. And now we again use our shift theorem. It's going to be e to the 3t to account for the s minus 3, and then just cosine t. All right, so it's quick once we get the hang of it. All right, now let's take a look at something that's a little bit different, or looks very similar, but has a little bit different flavor. All right, so let's now try to find the Laplace, which function has the Laplace transform of 1 over s squared minus 6s plus 8. So this is plus 8 instead of plus 10. You wouldn't think that that changes things very much, but it turns out that it does. And it, for reasons that we'll get into probably some other time. Basically, we have a couple of options here. Let's try option 1, which is completing the square. So what do we do in this case? Well, just like before, we're going to say, oh, well, we have 1 over s squared minus 6s plus 8. That's equal to 1 over s squared minus 6s plus 9 plus 8 minus 9. So 1 over s minus 3 squared minus 1. So the difference here is the minus sign. This does not fit the pattern for cosine or sine, but it does fit the pattern for the hyperbolic sign. So if we look in the table, we see this thing, sine h of alpha t has a Laplace transform equal to alpha over s squared minus alpha squared. So that's promising. That's something that we can possibly use. So let's go ahead and try it. If we try to do the inverse Laplace transform of 1 over s minus 3 squared minus 1, then this formula tells us that it will be equal to e to the 3t, because of the shift, times whatever this thing is, hyperbolic sine of t. And that's it. We're done. That's using the table. But of course, it's not very satisfying if you don't recall what the hyperbolic sign is. So just a quick review. So what are these things? What are what we pronounce as sinh t and cosh t? And they are what are called the hyperbolic sine and hyperbolic cosine. And by definition, they're not sines and cosines. They are these things. So sine, the hyperbolic sine of, well, let's make it a little more general. Let's make it the hyperbolic sine of alpha t is equal to e to the alpha t minus e to the minus alpha t over 2. And the hyperbolic cosine of alpha t is equal to e to the alpha t plus e to the minus alpha t over 2. They're just very convenient, it turns out, especially in this context. They have some nice properties that are very similar to sine and cosine, and that's how they got the names. These are just exponential functions that have been combined together. But it turns out, for example, that if you take the hyperbolic sine and you take its derivative, you get the hyperbolic cosine. If you take the hyperbolic cosine, you take its derivative, you get the hyperbolic sine. No minus signs like with sine and cosine, so just they switch back and forth between each other. And also, it has some things that are similar to sine and cosine in other ways. You have sinh of 0 is 0, and cosh of 0 is 1, just like sine and cosine. All right, so that's just a quick little primer on those guys. But so we can write our answer in this way. Okay. But if we do that, then we might also notice that this is equal to e to the 3t, by definition, times e to the t minus e to the minus t over 2. So that becomes 1/2 e to the 4t minus 1/2 e to the 2t. All right, so alternate way of writing the same solution. Now, I said that we had two options for this problem, and indeed we do. So let's try now to do option 2. Convenient, gave us the same page again. Awesome. So option 2, well, let's do it in black though. Option 2 is to use partial fractions, which we will be covering in a separate video in much more detail. So the idea here would be, instead of trying to do completing the square on this function, we might instead just factor it. S squared minus 6s plus 8, we get 1 over s minus 4 times s minus 2. And the idea of partial fractions is that this can always be written as something over s minus 4 plus something else over s minus 2. And so let's figure out what those things are. And then these two things that are being added together here, these are easy to find the inverse Laplace transform of. And since the Laplace transform is linear, we can just do the two individual things and then add them up. So how do we figure out what the parts are, what's A and what's B? It's like undetermined coefficients in a way. So we combine them back together into a common denominator. So this is A times s minus 2 plus B times s minus 4 over s minus 2, s minus 4, s minus 2. And so that leads us to, since these equations are the same, then and the denominators are the same, then their numerators must be the same. And this is something that's supposed to be true for all t values. So we get 1 equals A times s minus 2, I should say s values, not t values, plus B times s minus 4. Okay, so we need to find A and B that make this equation true. We can do this in a couple of ways. We can multiply it out and compare the coefficients on the s's or on the constants to get a couple of linear equations, or we can try just plugging in convenient values for s. So for example, if we let s equal 2, we get the equation 1 equals 0 plus negative 2b. So we get that b has to be equal to negative 1/2. And if we let s equal 4, we get 1 equals 2 times a. So a has to equal 1/2. So putting that all together, the inverse Laplace transform of 1 over s squared minus 6s plus 8 must be equal to the inverse Laplace transform of 1/2 over s minus 4 minus 1/2 over s minus 2. And by linearity, we get that this is equal to 1/2 times the inverse Laplace transform of 1 over s minus 4 minus 1/2 times the inverse Laplace transform of 1 over s minus 2. And we know what those are. That would be 1/2 e to the 4t minus 1/2 e to the 2t. And if you compare, that's exactly the same answer we got the other way, although it was written in a different form using the hyperbolic sign. All right, that's it for this time. I hope it's helpful. I'll be doing more examples of inverse Laplace transforms and also more examples of partial fractions, because partial fractions can get a little bit more complicated if we don't have just distinct linear factors.